Welcome to our channel Circuits Analytica. In this video, we will discuss the operation of an RC coupled amplifier. A bipolar junction transistor is used to amplify signals of very low amplitude. To operate as an amplifier, a BJT can be used in any one of the three configurations: common emitter, common base, or common collector configurations. Usually, a common emitter configuration is used to amplify signals of very low amplitude due to its high gain when compared with the other two configurations, common base and common collector configurations. To operate a transistor as an amplifier, it must be in active region. The base emitter junction must be forward biased and collector base junction must be reverse biased. There are different types of biasing circuits like fixed bias circuit, collector to base bias circuit, voltage divider biasing circuit, etc. to keep a transistor in the active region. The most preferred type of biasing is voltage divider biasing with emitter resistance Re, as operating point is more stable when compared to the other biasing circuits. This is the circuit diagram of a RC coupled amplifier. Voltage source VCC bias the transistor in active region. Base emitter junction is forward biased and collector base junction is reverse biased using voltage source VCC. There are resistors R1, R2 and Re. Resistance R1 and R2 provides voltage divider biasing and resistance Re provides stability against any variations in the device parameter like beta and leakage current. Resistance RC is the DC load of the amplifier through which DC current flows. There are two coupling capacitors CC1 and CC2. Coupling capacitor CC1 couples input signal to the input of the amplifier and coupling capacitor CC2 couples output of the amplifier to the load resistance RL. Capacitor CE is the emitter resistance bypass capacitor. Emitter resistance bypass capacitor is connected across the emitter resistance so as to bypass AC current flow through the emitter resistance Re. So if AC currents flows through emitter resistance Re, that leads to a negative feedback which will reduce the gain of the amplifier. DC analysis of a circuit. For a DC analysis of any circuit, replace all components in the circuit with its DC equivalent. The major components whose behavior depends on frequency are capacitors and inductors. The behavior of capacitors for DC signals is open circuit. Capacitive reactance is inversely proportional to frequency and frequency of DC signal is equal to 0. So for DC signals, capacitive reactance is equal to infinity or open. And inductors behaves as short circuit for DC signals. Value of resistors are independent of frequency. So this is the RC coupled amplifier for which we are going to do the DC analysis. replace all frequency dependent components with its DC equivalent. So here there are three capacitors which are frequency dependent. So coupling capacitor CC1 is replaced with an open circuit. So now input signal Vs is disconnected from the input of the amplifier. Coupling capacitor CC2 acts as an open circuit for DC signals, so load resistance RL is disconnected from the circuit, and bypass capacitor CE also acts as an open circuit. So bypass capacitor CE is also replaced with its DC equivalent. So now if we redraw the circuit becomes like this. Resistance R1 and R2 forms the voltage divider biasing circuit, and resistance RE provides stability for the biasing circuit. To analyze the operation of this circuit for DC signals, we have to apply Thevenin's theorem. So when we apply Thevenin's theorem, the circuit shown on the left hand side becomes as shown on the right hand side. Now we are going to apply Thevenin's theorem. Divide the network into two different networks, network A and network B. Disconnect network B from network A. Find the Thevenin equivalent voltage VTH and Thevenin equivalent resistance RTH for network A. So let us find the Thevenin equivalent voltage. Thevenin equivalent voltage VTH is the open circuit voltage of network A, which is nothing but the voltage drop across resistance R2. So VTH is equal to IR2 into R2, and IR2 is equal to VCC divided by R1 plus R2. Therefore, we can write VTH is equal to VCC divided by R1 plus R2 into R2. Now to find the Thevenin equivalent resistance RTH, replace the voltage source with its internal resistance. Internal resistance of a voltage source is equal to 0, and find the effective resistance which is seen when we look into the output terminals of network A. So RTH is equal to R1 parallel to R2. We can write RTH is equal to R1 R2 divided by R1 plus R2. Now let us apply KVL to the base emitter loop after replacing network A with its Thevenin's equivalent. VTH minus VRTH minus VBE minus VRE is equal to 0. VRTH is equal to IBQ into RTH. VRE is equal to ICQ plus IBQ into RE, where IBQ is the base current when no input signal is applied, and ICQ is the collector current of the transistor when no input signal is applied. So we can write VRE is equal to beta IBQ plus IBQ into RE. Or we can write VRE is equal to 1 plus beta into IBQ into RE. So we will get VTH minus VBE minus beta IBQ plus IBQ into RE minus IBQ into RTH is equal to 0. We will get IBQ is equal to VTH minus VBE, the whole divided by 1 plus beta into RE plus RTH, equation number 1. Now apply KVL to the collector emitter loop of the circuit. VCC minus VRC minus VCE minus VRE is equal to 0. VRC is equal to ICQ into RC and VRE is equal to ICQ plus IBQ into RE. So VRE is equal to 1 plus beta into IBQ into RE. And VRC can be written as beta IBQ into RC. VCC minus VCE minus beta IBQ plus IBQ into RE minus ICQ into RC is equal to 0, where ICQ is equal to beta into IBQ. Finally, we can write VCE is equal to VCC minus 1 plus beta into IBQ into RE minus ICQ into RC, where ICQ is equal to beta IBQ. DC load line of the RC coupled amplifier. So DC load line is a graph which is plotted on the output characteristics of the transistor. So here the output parameters are VCE and IC. VCE is plotted along the x-axis and IC is plotted along the y-axis. So we know that VCC is equal to ICRC plus VCE plus IERE. So we can approximate IC as IE. Therefore, we will get VCC is equal to ICRC plus VCE plus ICRE. So in this equation, if we put VCE is equal to 0, we will get the maximum value of collector current IC. IC is equal to VCC divided by RT, where RT is equal to RC plus RE. In the equation, VCC is equal to IC into RC plus RE plus VCE. If we put IC is equal to 0, we will get VCE is equal to VCC. So first point is located on the y-axis and the second point is located on the x-axis. Combining these 2 points, we will get the DC load line. The operating point Q is fixed in such a way that VCEQ is equal to VCC by 2. So plot the operating point Q in such a way that VCEQ is equal to VCC by 2 and find the value of ICQ. Using the equation, VCC is equal to IC into RC plus RE plus VCE. Now we will do the AC analysis of the circuit. For AC analysis of any circuit, replace all components in the circuit with its AC equivalent. The major components whose behavior depends on frequency are capacitors and inductors. All capacitors are replaced with short circuits. All DC sources are replaced with its internal resistance. So all DC voltage sources are replaced with short circuit and all DC current sources are replaced with open circuit. So this is the circuit diagram of the RC coupled amplifier for which we are going to do the AC analysis. So in this circuit, there is only one DC source, a DC voltage source VCC, and there are 3 frequency dependent components, 3 capacitors CC1, CC2 and CE. So step 1, replace VCC with a short circuit. Step 2, replace capacitors CC1, CC2 and CE with a short circuit. So this is the circuit diagram of the RC coupled amplifier after drawing the AC equivalent circuit. So redrawing the circuit becomes like this. RP is equal to R1 parallel to R2 and RL dash is equal to RC parallel to RL. So this is the diagram of the RC coupled amplifier where the transistor is replaced with its hybrid pi model. Yellow colored box denotes the hybrid pi model of the transistor. So we are going to apply sine wave signal as the input to the RC coupled amplifier. So we will start with the positive half of the sine wave. During positive half of the input signal, current flows through the coupling capacitance CC1 towards base of the transistor, resulting in an increased base current. So total base current of the transistor becomes IB is equal to IBQ plus red IB. So the first term IBQ is the DC component and red IB is the AC component. Variation in base current due to the input signal Vs. So collector current of the transistor becomes ICQ plus red IC. So ICQ is the DC component of the collector current and red IC is the AC component. Variation in collector current due to the input signal Vs. When collector current varies, that results in a variation in the voltage drop across collector resistance RC, and this results in a variation in collector emitter voltage drop. So variation in collector current results in a variation in the collector emitter voltage drop, and this variation in collector emitter voltage reflects in the voltage across resistance RL through coupling capacitor CC2. So this is the diagrammatic representation of the circuit during positive half. There are two components for the base current, IBQ and small ib, which is shown in the red color. So the AC component flows from input signal towards base of the transistor. During negative half of the sine wave, current flows through the coupling capacitance CC1 from base of the transistor to the input signal, resulting in a reduction in the base current. Total base current becomes IB is equal to IBQ minus red IB, where IBQ is the DC component and red IB is the AC component. This reduction in base current ultimately reflects in collector current also. Collector current also varies. Collector current IC is equal to ICQ minus red IC, where ICQ is the DC component and red IC is the AC component. So variation in collector current results in a variation in the collector resistance voltage drop, which results in a variation in the collector emitter voltage of the transistor. And variation in collector emitter voltage of the transistor reflects in the voltage drop across resistance RL through coupling capacitor CC2. So during negative half of the input signal, current flows through coupling capacitor CC1 from base of the transistor to input signal Vs, resulting in a reduction in base current. and this reduction in base current results in a reduction in collector current. The reduction in collector current results in a reduction in the collector resistance voltage drop, which reflects in the collector emitter voltage drop, and the variation in the collector emitter voltage drop is coupled to the load resistance RL through coupling capacitor CC2. Voltage gain of a RC coupled amplifier. For any network, voltage gain is defined as the ratio of output voltage to input voltage. In the case of a RC coupled amplifier, input voltage is applied between base and emitter. So Vs is equal to VBE, and output voltage is taken between collector and emitter. V0 is equal to VCE. Output voltage V0 is the voltage drop across resistance RL dash due to current IC. So this is the small signal equivalent circuit of the RC coupled amplifier. So here we can write base current IB is equal to Vs divided by HIE, equation number 1. Collector current IC is equal to HFE into IB, equation number 2. Now output voltage V0, look at the polarity of output voltage V0. Collector of transistor is positive with respect to emitter of the transistor. This polarity is possible if and only if current flows through resistance RL from collector to emitter. That means current flow through RL dash is equal to minus IC. So we can write VCE is equal to minus IC into RL dash, where RL dash is equal to RC parallel to RL. Output voltage V0 is equal to VCE, which is equal to minus IC into RL dash. We know that IC is equal to HFE into IB. Therefore, we can write V0 is equal to minus HFE into IB into RL dash. We also know that IB is equal to Vs divided by HIE. Therefore, we can write V0 is equal to minus HFE into Vs by HIE into RL dash. So we know that voltage gain AV is equal to V0 divided by Vs. So we will get voltage gain AV is equal to V0 by Vs is equal to minus HFE divided by HIE into RL dash. Input and output impedance. Input impedance is defined as the ratio of input voltage to input current when output terminals are shorted. So we will get Rin is equal to HIE in shunt with R1 in shunt with R2. We will get input impedance Rn is equal to HIE parallel to R1 parallel to R2. Output impedance is defined as the ratio of output voltage to output current when input terminals are open. So we will find that output impedance R0 is equal to RL dash. Thanks for watching Circuits Analytica. Enjoy learning.